Okay, so we're going to look at financial maths, and in particular questions that involve geometric series, and as a result we can make use of the sum to n terms of a geometric series formula, which is a on 1 minus r to the n over 1 minus r, where a is the first term and r is the common ratio, what's being multiplied by each time to get the next term in the sequence or series. In addition to that formula, we also want to have some familiarity with the formula for compound interest, which is that the final amount is equal to the principal, the starting amount, on 1 plus the interest rate to the power of t. So, other than those two formula, one of the things we're interested in is whether we have what I would call savings type questions, where we're finding the future value of regular installment savings, or are they loans type questions, in which case we're finding the present value of a series of repayments, and we'll talk about each one as we do it. So the first two questions we're going to look at are going to be savings type questions, let's call them. Okay, so this first question, we're told that there's a building society. It's offering a savings account that has an AER, so annual equivalent rate, so basically a yearly interest rate of 4%. So if a customer saves 5,000 per year, per annum, starting now, how much will the customer have in 5 years' time? Now look, if you have 5,000 and you save it for 5 years in a row, we would expect by the end we'll have at least 25,000. But remember that the bank will give you interest on each of those 5,000s. The thing about a question like this is the first 5,000 that you saved will get more interest than the last 5,000 that you saved. So what we should do is we write out a series. So I'm going to say 5,000 at the start of year 1, and then 5,000 at the start of year 2, and 5,000 at the start of year 3, and so on. If it's only 5 years, it actually is no harm. We could write them all out. So these are the 5,000 payments. But obviously if this is a longer period of time, or if we get interest monthly, in which case the 5 years by 12 months, there would be 60 interests, or 60 periods of interest. We obviously wouldn't write them all out. And what we would have is, we'd have a gap in the middle with dot, just to show that there is that many terms in the series. Okay, well this first 5,000, it's going to stay in the bank, and if I use this compound interest formula up here, it's the principal, 5,000. It's going to stay in the bank, so 1 plus 0.04, that's the interest rate as a decimal, and it's going to stay in the bank for the full 5 years. Then we're going to come along and we're going to put 5,000 in the bank, but it's only going to stay in the bank for 4 years. So you can see the 1 plus I'm just going to say that that's 1.04. So that's going to stay in for 4 years, get 4 years worth of interest. And the next 5,000 is going to stay in for 3 years, get 3 years worth of interest. The next 5,000 is going to stay in for 2 years, so 1.04 to the power of 2. And then the last 5,000 you put in the bank, that's only going to stay in the bank for 1 year, so to the power of 1. Now look, this is only 5 payments. I could easily just put the sum of these 5 in the calculator now and I'll get my final answer, which will be more than 25,000. But we're trying to set this up in a way of that this could be 60 of these in a row, or the sum of 60 payments. And so we wouldn't be able to write them all out, we wouldn't be able to put them all in the calculator. So we set this up as a series. And what kind of a series is it? It's a geometric series, where the first term, A, is obviously 5,000 on 1.04 to the power of 5. And then R, well, what are we multiplying each time by to go from one term to the next term? We can actually see that the 1.04s are going down by a power each time. So we must be multiplying by 1 over 1.04. Now, if you're ever not sure, if you want to find R in a geometric series, we take the second term and we divide it by the first term. So if we took the second term, which is 5,000 on 1.04 to the power of 4, divided by the first term, which is 5,000 on 1.05 to the power, 1.04 still, to the power of 5. Well, if we divide above and below by 5,000 by 1.04 to the power of 4, we would be left with 1 over 1.04, which is what we have here as our R term. Okay, so how many payments is there? Well, this is 5 lots of payments or 5 lots of savings, so n then is equal to 5. And we take our Sn formula, which is up here, and we write it down. So Sn is equal to the first term on 1 minus r to the power of n over 1 minus r. And the S of 5 would be equal to A, which is 5,000 on 1.04 to the power of 5, on 1 minus r, which is 1 over 1.04 to the power of 5, and that's all over 1 minus 1 over 1.04. Okay, so that's the setup. I'll throw this into the calculator in a second and we'll see what our final answer is. But that's how we would set up a question like that. So we'll just quickly put up the solution rather than waiting for me to throw it into the calculator. And our answer is 28,164.88. So we can see that over the period of time, we said that 5,000s is 25,000. We gained 3,164 euros and 88 cents in interest. Now, how do they make these a bit more difficult? Well, a couple of ways. The first thing is they might not tell us what the regular amount is that we're saving, and then we would call that P. But they might give us the final amount. They might say that this sums to 28,164.88 after 5 years. What must the P value have been? So we would set this up the same way. We'd have a P here. We let that equal to 28,164.88. We'll throw the whole left-hand side into the calculator, and then we'll divide that into the 28,164.88. The second way they'll make it more difficult is if they give us a yearly interest rate, but then tell us that it's compounded monthly. In that case, what we have to do is we'd have to change the yearly interest rate into a monthly interest rate. Well, given that if the question says that they're going to save monthly, if the amount that they save is per month as well. So let's have a look at a question like that. So this is our first one, fairly straightforward. We're kind of working forwards in this, putting the numbers into the formula and working it out. If we have a look at this question here, we'll see how we can ask it slightly different. Here what we're doing is we want to save an amount for a number of years so that after the time we have 30,000 in the bank. So after 5 years savings, we have 30,000 in the bank. And the question is, firstly, how do we change a yearly interest rate, 2.75%, into a monthly one? It's definitely not as easy as just dividing by 12. We don't do that. What we do is we set up our formula, F equals P on 1 plus I to the power of T. So that's the compound interest formula. And what we say is, well, what would €1 turn into after 1 year at 2.75% interest? Well, the final amount, if you were to save €1, if that was the initial amount, €1, it would turn into 1.0275 after 1 year. Now, the question is, what's the interest rate, the I, if we were to compound that monthly, so to the power of 12? So if we manipulate this formula, we get the 12th root of 1.0275. That would be equal to 1 plus I. And then we subtract 1 from that. So I is equal to the 12th root of 1.0275 and then minus the 1. So that's the way that we turn a yearly interest rate into a monthly one. So we have to read the question carefully. It says the rate of interest per month that would be equivalent to 2.75%. And again, it's the 12th root of 1.0275 minus 1. And we get this monthly interest rate, which is 0.2263% per month. Now, how much must be deposited each month for 5 years so that we have 30,000 at the end of it? So we set it up similar to before. The first thing we have to do, though, is say that 5 years is 60 months. So there's going to be 60 periods of saving. We're going to save the same amount for 60 months, and at the end of it, when we factor in the interest that would have been earned on each of those amounts, it has to add up to 30,000. So the way we would do this, and we have to be careful when we read the question, it says that it's deposited, there's kind of savings or money deposited at the end of each month. Now, in our last example, we saved an amount at the very start of the first month. Here, we're not depositing money until the end of the first month. So that first amount of money, which I'm going to call P, that's going to get at 1.00, I have to check what the interest rate was per month, 1.002263. So 1.002263. That's only going to get 59 months interest. And then there's going to be another amount, that exact same amount of money is going to be saved, and it's going to get 58 months interest. And keep saving until the very last amount that we save, which is P, or the very last amount that's deposited, P, that doesn't get any months interest because we're depositing money at the end of the period of time, so at the end of the month. So the end of the last month, the savings is up, and the sum of these amounts of money have to add up to 30,000. So it is the same setup as we just did. Just be careful if your saving starts at the start of a month or an end of a month. That'll affect your first power, and it'll also affect whether the last amount gets a month's interest, so the power of 1, or if it's just a solitary saving of P. Now, what we're going to do is we're going to write down our A and R as before. So this is our series. So A is going to be the first term. So again, this is A. And R is going to be 1 over 1.002263. I haven't got the second term written here, but let's write it. P on 1.002263 to the power of 58. How do we go from a power of 58 to a power of 59? Well, we divide by 1.002263. Even though the first power is 59, we still have 60 payments. It's just that the last payment didn't get any interest, but there still is 60 amounts of P that are being saved to make the 30,000. So we pop A and R and N into our formula. So this is our SN formula. So here's our A, and here are our R's, and we have obviously the power is the N value, which is 60, and we let that equal to 30,000. And we take out our calculator, we put all of this in the calculator with the exception of the P. We bring the P outside and we multiply everything else in here, or we enter all this rest of the stuff into the calculator. And then it's that amount P is equal to 30,000. So 64.1865539.6p equals 30,000. Divide 30,000 by that amount, and you get €467.39. So that's how much we have to save for 60 payments to get an amount of 30,000. Now the last question is, how much interest will have been earned? Well, if we multiply 46739 by 60, we can see that 467.39 by 60 is €28,043.40. So we only deposited that amount of money, and yet by the end of it we had 30,000. So we must have earned €1,956.60 interest. Okay, so 2 examples of a savings question. Slight differences in each. The second example has a monthly savings and it has a monthly interest rate, and it also has this thing of depositing the first amount of savings at the end of the month, which is unusual. Normally the savings starts at the start of the month and the power is the same as the end value. Okay, let's have a look at a couple of loans questions. So we'll go back here. We'll do the same thing. So we look at an easy one where it's a yearly interest rate, and then we look at something a little bit more tricky. Now remember, with a loans question, we also have the amortization formula that we can use. You can only use the amortization formula in a loans question if the repayments of the loan are at the end of the month. If they're at the start of the month, we can't use that formula. So let's see if this is okay for this one. So there's a loan of 150,000. It's taken out at an annual interest rate of 3%. How much should the annual repayments be if the loan is to be repaid over 10 equal installments? Now look, someone will come along and say, well, you're borrowing 150,000, you're going to pay back over 10 equal payments, surely each payment will be 15,000. But it doesn't work like that. That doesn't factor in the time value of money, the fact that in 10 years time when you give back a repayment of 15,000, that's going to be worth much less in today's money. The buying power of that 15,000 in 10 years isn't like what it is today. So what we do instead is we write down that we're going to pay them back A at the end of the first year, we're going to pay them back A at the end of the next year, A at the end of the following year, and then we're going to keep paying them back values of A, or an amount of A, until the last year. In 10 years time, this will be the 10th payment of A that we'll give back to the bank. And it's the net present value of these repayments, or sorry, the net present value of these amounts A, that is equal to what the bank gave us in today's money. So we need to figure out what all of these values of A are worth in today's money. In today's money, that's when we're getting the 150,000. So how do we do that? Well, we use the compound interest formula, which is the final amount is equal to P on 1 plus the interest rate to the power T, and we rejig it to make a formula for the net present value. The net present value of an amount of money is going to be, let me just see this, F, the final amount, divided by 1 plus I to the power of T. So this amount of A that I'm going to give back at the end of this year, in today's money, that's worth A over 1.03 to the power of 1. Then I'm going to give them an amount A next year, the end of next year, and in today's money that's worth 1.03 to the power of 2. Then I'm going to give them back an amount of A the following year. I need to figure out what that's worth in today's money, so I discount it back by 3% for 3 years, and so on until I come to the last amount in 10 years' time. I'm going to give them back an amount of money. It's still A, but what is that worth in today's money? It's A divided by 1.03 to the power of 10. And it's the sum of these net present values, the sum of what those values or those amounts of A are worth in today's money, that has to be equal to the 150,000 that you're getting for your loan, or getting as your loan today. Now, we use the SN formula, so the SN formula is equal to A on 1 minus R to the N over 1 minus R, where A is the first term, so A is equal to A over 1.03, and R is equal to, well, what are we multiplying each term by to get the next term? Well, we can see the top, the numerator is staying the same, but the bottom is being multiplied by an extra 1.03 each time. So we're multiplying by 1 over 1.03. The number of payments or repayments is 10, and we're going to sub all these into the formula, let it equal to 150,000, and then we're going to solve for A. So let's have a look at what it looks like. So there's our sequence, our series. A is A over 1.03, R is 1 over 1.03. There's our SN formula, and we're going to sub in A is equal to A over 1.03, and then R is 1 over 1.03. When we throw that into our calculator, we get 8.5302. Obviously, we take this A outside the front, we can't put that into the calculator, and we just leave a 1 here. So that A doesn't obviously go into the calculator. When we do that, we get 8.5302A. We let it equal to 150,000, and now we divide 150,000 by 8.5302, and we get that the amount we have to repay to the bank every year for the next 10 years is 17,584. And that makes sense. Like we said, that if you had 150,000, you were borrowing, and you give 10 repayments back, maybe it makes sense that each one would be 15,000. No, it needs to be more than that, because you need to account for the time value of money. That amount of 17,000 that we're going to give back in 10 years' time, that's worth much less than 17,000 in today's money. The other way you could do this question, and look, most people will probably just attempt it this way, is because we're paying back an amount of A at the end of each month, we can use the amortization formula. So the amortization formula is in our tables, where A is equal to, A being the loan repayment, is equal to P, the amount we borrowed, on the interest rate on 1 plus I to the power of, now this N, that's a T, so the period of time, which in this case is 10, over 1 plus I to the power of T minus 1. So we're just going to sub in P, which is 150,000, I, which is 3%, and T, which is 10, and then we just throw that into our calculator, and we get the exact same amount. Okay, so it's the exact same number, but we can only use this formula here when we're repaying the loan at the end of the month. It doesn't work if you repay it at the start of the month. Now, it doesn't make sense anyway in life to borrow an amount of money of 150,000 and make a repayment straight away. Like, that doesn't make sense. So normally loans questions, the repayment amount is at the end of the month. Okay, we'll do the same question, and like before, what's different, or what could we be asked that's a little bit different? Well, we could be asked to repay back an amount every month, which is the normal way you would pay back, let's say, a mortgage. And then obviously the yearly interest rate that we have of 1.03, we'd have to turn that into the equivalent monthly interest rate. So we'll have a look at an example from an exam paper. So a couple agreed to take out a 250,000 mortgage. So they're getting that mortgage today, and the loan is going to be paid back monthly, that's very important, over 25 years. Now here they actually give us the monthly interest rate. We didn't have to take a yearly one and work it out to be a monthly one. They just gave us the monthly interest rate, so it's less than 0.3% per month they have to pay back. What we do have to do though is realise that 25 years, if we have to turn that into months. So 25 times 12 is equal to 300 months. So could we use the amortization formula for this? Yeah, we're repaying the loan at the end of each month. We have a monthly interest rate. We have a 250,000, which is our P value. So if we pop these into the formula with the N value of 300, that's the period of time. The amortization formula just tells us that we'd have to repay 1,244.06. Now it's important that we look at this question as well by setting up a geometric series, because they may say in the exam, by setting up a geometric series, show that the monthly repayment is 1,244.06, or find the monthly repayment using a geometric series rather than the amortization formula, which we did there. So let's see how we use the setup with the geometric series. So the sum of the present value of the repayments, we're going to call the repayments A. And so there's going to be, what did we say, 300 payments of A. We're going to repay back 300 payments of A. And it's the net present value, what all of these values of A are worth in today's money, that should be equal to the amount we got, which is 250,000, because we were given that amount today for the mortgage. So if we have a look at what that looks like, so the first amount that we're going to pay back at the end of the first month is going to be A over 1.00287. That's the net present value, or the value in today's money of that amount we're paying back. In 2 months' time, we're going to pay back an amount, and we want to find out the net present value of that amount of money, so that's A over 1.00287 squared. Until 300 months time, which is in 25 years, we're going to pay back our final amount of A, and it will be worth so much less in today's money than what A is worth today. And the way to figure out how much it's worth in today's money is to discount it back by 300 months, and it's the sum of the net present values of all those amounts that are equal to 250,000. So we pop them into this formula. What's A? A is A over 1.00287. What's R? Well, to get to the next term, we're clearly multiplying by 1 over 1.00287, and N is equal to the number of payments, which is 300. So we pop them into the formula, and we can't put the A into the calculator, so we replace that with a 1, and we imagine that the A is outside of all this. We put everything else into the calculator and let it equal to 250,000. So when we put it into the calculator, we get 200.95. A is equal to 250,000. Divide 250,000 by 200 by 0.95, and we get that A is equal to 1,244.06, which is exactly the same amount as when we had used the amortization formula before. So look, that's the two setups. We have savings questions, we have loans questions. Within both of those setups, we can be asked questions that are either being repaid or saved yearly, or ones that are being repaid or saved, repaid monthly. So just know the difference between each of those and how to do that kind of a question. Okay.